All right, pre-calculus. I have a limited amount of time. I've got 15 minutes. Let's see how many we can go through. All right, and talk about, I haven't even looked at these, but I got my calculator at the ready because a lot of these problems may involve some calculator stuff. Identify whether each scenario represents exponential growth, starting low and then going, or starting high and then approaching nothing, exponent for decay, or neither. The volume of a cube, oh boy, as the side length grows, well, you know, thinking about that, volume is equal to, it says as, now it's a cube, all the sides are the same, so we would have a length times a width times a height, and if we were to take that and let's say double each one, let's say that, and then maybe triple each one, quadruple each one, so I'd be taking the number 2. I'd be taking a number like the number 2 and then using it 1, 2, 3 times, and then be taking the number 3 and using it 3 times, and 4 and then multiply. Yeah, all right, so when I look at this one feels like it's a neither. It's because when we think about it, the variable for y, a, b to the x needs to be there. The thing that needs to change needs to be the power. And what I'm seeing is the base is the part that's changing, not the power. The power is staying the same every time. All right, so the price of a shirt, by the way, I feel pretty happy that, got that one. All right, so the price of a shirt with 40% off coupon. Okay, well, I mean, really, you're using that, you're taking 100% minus the 40%, you're gonna pay 60%. So 0.60 is gonna get multiplied times whatever the price is, but that's only gonna be used once. So that's a neither. What are they doing to us here? Well, they're trying to trick us with a couple things that look like they could be. All right, reselling value of a car based on its age and years. That's definitely going to be some sort of decay problem. You know, the price of the car, the starting price of the car is going to get multiplied by some decay factor each year, each time. All right, anyway, let's move on. All right, so the number of students enrolled at a certain university increases by 3% each year. I like that, 3% each year, so that's 0.03 is the number that we're going to be using, and we're going to be adding that on. It's increasing, boom, boom, boom. All right, so in 2010, is that year 1? Let's see. In 2010, the university has that many students. Is that a starting value? Write an equation for a function n of t that models the number of enrollments per year where t is the time of year since. There we go. So there's year 1. So we have the 27,360 students. But next year, it'll get multiplied by 1.03 to find the next year. And then the year after that, and the year after that. And so we'll have, what are we using here? T for the number of years. So we'll have n of t is equal to that. There we go. All right, that's not that bad. Determine if each equation represents exponential growth. Again, without even looking at them, or decay, or neither. I am looking for a base number that is multiplied by a growth factor, and I'm looking for the x, the t, the anything, the variable right here, so that, what is it? Yeah, our independent variables here. All right, anyway. Okay, we got a starting value times a growth factor, and yep, absolutely. Looking at this one. The power here is not an x, so that fails. B fails. We have a power to the x, we have a starting value and a growth rate raised to a power, and they are being multiplied together. Now, if they had put a plus sign between this, that wouldn't be. Well, yeah, it could be, because that plus value, this then wouldn't be the starting amount. That would, adding any amount onto this would just shift the graph up or down. So really, this is the part that makes it exponential growth or decay. Remember that our y equals b to the x, some growth factor, that's our parent function. There doesn't have to be a number in front. All right, anyway, yes. So yes, so 3 out of the 4 are exponential. Let's move on. Did it say to do anything else? It said to give a reason for your answer while I'm talking it out. All right, number 4. I'm going to zoom in just a bit. All right, select values of an exponential function. Okay, so if this is an exponential function, then what we're going to have is we're going to have a starting value multiplied by a growth rate each number of times. So this would be multiplied once. So taking this, the new value of 36 compared to the old value of 24, 30, I know, we just need to see it. We got 1.5. So if I take 24 and I multiply it by 1.5 and continue multiplying by 1.5, then that will be my growth rate, okay? And so select values that would make, well, if I take that 24 divided by 1.5, I get 16 would have to be this value, and now I have to work out the rest of these. 36 times 1.5 is 54. 54 times 1.5 is, yeah, 81. Okay, and 5 times 1.5, boom, 121.51, 21.5. Okay. An exponential function is it passes through, there we go, passes through these. So we don't necessarily have an a value, but we can find it. All right, so looking at this, how many steps go by? All right, it's from 2 to 3. That's a change of 3. Okay, so that's important. That means that our power, some number has been used the power 3 times. That a growth rate has been used 3 times to go from 40 down to 5. It's been decaying, so it's lost 35. But this is like a multiplication problem. So as we take this and we work this down, 35 compared to the original value of 40. So down, no, 5. Let's take that. 5 divided by 40. All right, so overall it's lost, it's the growth rate, 1, 2, 5, 4, 3 times has been this. Okay, so here, let's change it. This is not what it is, but some growth rate, some x that's been used 3 times gives us 0.125. Okay, so really, what do I have to do? I've got to take the cube root of that. Let's see. So I need the cube root of 0.125. Okay, and we get 0.5. We get a half. Just double checking. Yeah, that matches up with the answer key. Great. Okay, so our decay rate in our in our function, we need an a and a b value. So y equals a times b to the x. So what we just found was we found that the b, we don't know the a yet, but we found that the b value is a half, 0.5 to the x power. Well, here's the thing. If at 2, something's getting cut in half, so we could have done that with a 40. 40 gets cut in half once to become 20, and then twice to become 10, and then a third time to become 5. So if we work the pattern backwards from 2, back 1 step, then we'd be at 80. So 240, 180, 0. We want the 0 number, would be 160. This is a way of working that backwards, 160. So there's our answers. There's our A, there's our B, talking it out and everything. Now, could there have been other ways to do that? Yeah, we could have put 0 in here for this, or solve with a known coordinate, take the 5 and the 5, put the 5 here and the 5 here, and solve it all algebraically. Put the 5 here and the 5 here and solve it algebraically for that number. Okay, number 6. Initially, a company sends a weekly newspaper to 65 people. 2 weeks after its launch, the company sends the weekly newspaper to 75 people. So over the course of 2 weeks, it went up 10. And so 10 out of 65, let's see, or let's do the 75 divided by 65. And that's a growth rate over 2 weeks of 1.15, but we kind of want, since that's 2 weeks, we want to take the square root of that, so this is going to be the square root of that answer. And so it has a weekly growth rate of 7.4%, 1.04. Okay, so assuming the number of people receiving, I don't even know what the question is asking, but assuming the number of people receiving the newspaper each week increases, linearly, write an equation for that. blah, 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 blah. And let's assume it increases exponentially. Well, linearly is saying that you're going from 65 to 75 people, so that's plus 10 people over 2 weeks, which is the same as adding 5 people in 1 week. So there's our rate of change. R of t is the number of people after the launch initially. So that's the launch. So slope intercept, we would have 5x or t, 5t plus the 65. That's our linear one, great. But if we would have n of t, thinking about this exponentially, it's going to be 65 gets multiplied by that growth rate, 1.074, all right, to the power of t. Now, there's another way that we could have done it. We could have written that it's equal to 65. I think it would work to write it as, remember when we did 75 divided by 65, we got this, 1.15. So we could just use 75 divided by 65, keep that exact answer, 75 divided by 65, to the t divided by 2. What does it mean to have a 1/2 power, a 1/2 power? That means to take the square root of that answer. When we take the square root of that answer, then raise it to the power each week, it's mathematically equivalent to this. Yeah, so, okay. And we could also write it as 65 times the ratio of 75 divided by 65, the square root of that answer, since it's by 2 weeks, to the t power. That's mathematically equivalent to all of these. Okay, all right. Which model do you think is more accurate? Depends on which, whether we think this grows linearly or, I'm not even going to answer that. Let's move on. It's more of an opinion question. All right, so number 7. The relationship linear, exponential, neither. So looking at these, we want to see, let's look at it. So this first one here, I'm seeing that every three, this is doubling. So there's an amount of time that's going by, and in that amount of time, a growth factor of multiplying by the same number is happening. That is exponential. That is exponential. When I look at this is going up by 4, -1, 0, 1, 2. That's not the same amount. So this is going up 4. Let's check this one. This one here is going up 4 as well. Here, is this multiplying? That's multiplying by 1/3. This is not multiplying by 1/3. So this one is not exponential, but I do see this is going down by 6, and that's going down by 6. So assuming that this pattern also holds here, that this one would be linear. Okay, and the last one. So I see we're going up by 2, going up by 1, going up by 2. I'm looking at these that are going up by the same amount, and seeing, is there a growth factor or decay factor? So 36 divided by 100, well, that'd be 0.36. 36 divided by 100, we know that. Will I get that same answer when I do 7.776 divided by 21.6? We get the same answer. So this one is decay. It is exponential. Let's move on. I told you I got 15 minutes on the clock. We're running out of time here, so I might not be able to go over all of them, but let's see. A new Ford Escape is valued. There we go. It depreciates by 8% each year, right? But do not evaluate an expression for 7 years. Okay, so 26010 times. It's losing, so it's going to be 1 minus 0.08 or 0.92. That's what you could have there, to the power of 7. Done. Let's move on. I'm flipping my answer key. So the amount of ibuprofen. Oh, I love these. These are my favorites. All right, I'm putting a star in it because I love this. The exponential growth or decay of medicine in somebody's body. I love that. The amount of ibuprofen in somebody's bloodstream is modeled by this. So 400 milligrams, and 71% of it remains. How many milligrams of ibuprofen are in one adult dose? Well, that's that starting amount. That's that 400. Okay. What percent of ibuprofen is eliminated? Well, 71% remains. So 100 minus the percent minus the 71% means that there's 29% loss or eliminated in in each amount of time, the hour. All right, and the last one, Duska drinks 12-ounce cup of coffee. Yeah, I love this. And then all right, has 142 milligrams of caffeine. After 1 hour, it approximately has that much. So there's our decay factor. The amount of caffeine is by a constant factor. Factor means multiplying, so that means exponential decay. So this situation, it models decay because it's going down. What percent of caffeine remains in the bloodstream? So let's take that 126.4 divided by the original 142, and it is there's our decay rate of 0.89. What percent of the caffeine remains? That's the percent, so 89%. About 89% is what remains. And write an equation function that gives the approximate number of milligrams per hour. Okay, we can do this. So the starting amount times that decay rate, 0.89, remember as a decimal. Let's toss in some more, to the power of t, and c of t equals that, and we are done. A minute over, but that's okay. I can still make my appointment. Take care, folks. Bye.